let's get this given to our other class. Good morning, everyone. Yes. Who dares text me? Oh, cool. You see that. Well, good. This is going to take forever, apparently. So, I can just do this later. In that case, let's go ahead. So, let's see. Last time we did some solution stoichiometry, right? There's a few more things that I have to talk about with solutions before we move on to thermochemistry. So, if you guys have any outstanding questions, of course, you are welcome to put them up there. We can address them, but otherwise, we will, keep on going. So I think yesterday we made like a 0.8 molar sodium chloride solution or something like that earlier, right? And we made like 500 mLs of solution or whatever. This is solution, by the way. You'll often see that abbreviation. How that actually works is we can't just take 25 grams of sodium chloride and dump it into 500 mLs of water, because of course that sodium does have a little bit of volume, right? And so by doing that, we would end up with more than 500 mLs of solution. So we have special pieces of glassware. Oh, this is kind of a bad drawing. Well, whatever. This is called a volumetric flask. Volumetric flask. And these are specific to whatever a particular volume. So in this case, this one would probably be a 500 ml volumetric flask. And these are specifically made so that there is a line kind of near the top of the flask that will tell you when you have 500 mils of solution. And so you can't just go ahead and fill this with water and then dump in your sodium chloride after. What you should always do is put your solutes in first. So that's the stuff that's going to dissolve. So in this case, that's the sodium chloride. And then you fill the flask with deionized water. That's water that is pure, dare we say. So, tap water or bottled water. No, computer, stop. I don't know if you heard that. It's pretty, apparently Alexa is very happy to answer questions. What was I saying? Oh yeah, like tap water and stuff, they all have dissolved ions in them. And so we have to use deionized water just to make sure that we don't have extra crap in the solution we're trying to make. And so the order of stuff we would do is we would put our powder in first, the salt, and then we would fill the flask up to the line. Sometimes you'll fill it up maybe like 80% of the way, and you'll kind of stir everything, make sure it dissolves, and then you'll just top it off up to the line. That's one way to do it too. I'll probably make a video of this so you guys can see, since I finally have access to the labs. But first I'll grade your homework. That's I'll do that first, and then we'll start making lab videos. So that's how you'll make a solution. So you'll see that on some of the homework, it's like you have these things available to you. How are you going to make this particular solution? It's important that you always do your solutes first and then add your water afterwards. Alrighty. We can also dilute solutions. And dilute just means make less concentrated. For example, if we had that 25 grams of sodium chloride in 500 mils of water, that was about 0.8 molar, I think we calculated yesterday. We could add more water to it. We could say, let's make this in 1,000 ml instead. And as a result, that one will have a lower concentration of our particular solute. And you know that, right? Like if you, okay, I've got my coffee here or whatever. If I add water to this, that's going to make it less concentrated, right? It's going to be weaker. It's going to be less strong. There's going to be less like coffeeness per sip, right? So the more solvent you have, the lower your concentration it's going to be, right? Because your concentration is moles of solute over liters of solution. So the more liters of solution you have, the less your concentration is going to be. And we see here that we have a handy-dandy formula that we can use to do dilutions with. And that's going to be how we are going to be able to calculate how much of a more concentrated solution we'll need, or what a new concentration would be, or whatever. What these mean they are concentration and volume. And so it's your set of concentration and volume at one group of conditions will be the same as the product if you dilute it or concentrate it, in either way. The reason for this is, notice that concentration is moles per liter, and we're multiplying it by liters, right? And so that's just moles, right? We're saying if you put 25 grams of salt in 500 mils versus 1,000 mils, you still have the same amount of salt, right? Your moles of NaCl do not change. We're just adding more water. And adding more water will lower our concentration, but it does not change the number of moles that we have. Right? We're still going to have 25 grams of sodium chloride. If we boil away all that water, we'll get our 25 grams back. Doesn't matter how much water we put in. However, it's going to lower the overall concentration if we put more water in there. And so, we can say, if I want how much, let's say, how do I make this? Let's do that. So I went to the chemical store and I bought 6 molar hydrochloric acid. But for a particular experiment, I only need 0.1 molar hydrochloric acid. And I need a particular volume of that. We can figure this out using this formula above here. What's good to know is it does not matter which one you put as 1 or 2, as long as they are consistent. So that means that this 250 mil and the 0.1 molar, those two numbers need to go together. So either make that M1 and V1, or make them M2 and V2, does not matter. But as long as they're together. And so I'll just do that, why not? So M1 is going to be 100 molar, and V1 was 250 mils. And then we know that we are starting with 6 molar hydrochloric acid, and we want to see how much of that is going to have the same number of moles, right? Because we're just going to dilute this. So doing this math, surprised Kevin hasn't already done it, 0.1 times 250 divided by 6. This tells us V2 is 4.16666 milliliters. How do we know milliliters, by the way? Easy. Molar cancels out. We're left with mils. And look at Star-Lord putting it into scientific notation and liters for us. It doesn't matter which particular unit this time, because actually yours would work just fine as well. So this tells us that we need, I'll just say 4.17, I'm going to round it. So we're going to need that much of our concentrated HCl. And in order to get to 250, how are we going to get that? So that means that this has to be the 4.17 mil of, oops, my gosh, that was just a disaster. Right, we know that we're going to put in a certain volume of hydrochloric acid solution, and the rest is going to be water. Now, I guess we could technically calculate, we could say, yeah, we're going to need 244.83 mils of water. But best way to do this, again, is to grab a volumetric flask, one that is set to 250 mLs, where the line is drawn there. One thing to note, so technically we would just combine them. We'd put our HCl in, we'd put the water in up to the line, and boom, we're done. However, one thing to note safety-wise, while we have not had the lab so far, is we always add acid to water, right? The reason for this is because when we dilute acids, they tend to put off a lot of heat. And so the more water we have, the less chance there is of, boiling over or something bad happening. And so probably what you'll do with this is you'll take, I don't know, maybe you'll fill this halfway with water. Always deionized. Then you'll add your 4.17 ml of hydrochloric acid solution. And then you would fill with water to the top, to the line, rather. Technically, you could do this for solid things as well. It's just acids in particular. You always want to have some water in there just to make sure that you don't have an explosion or anything like that. So this is how you would go ahead and dilute this solution. And doing so, you would end up with 250 mils of your diluted HCl, which you can then do whatever you're doing with that. Okay, questions on that? Okay. Last thing that I want to just quickly go over is just making sure we remember. I did put this as part of like the homework like explanation or whatever. Just so we are all super clear about this. What this means when we actually have a solution of a concentration that is of an ionic compound, remember ionic compounds will split into their ions. And so we remember that calcium chloride will split into 1 calcium and 2 chlorides. So if we had 0.1 moles per liter of calcium chloride, we're going to have the same number of moles of calcium ions, and we're going to have twice as much of chloride. And that's, again, just because of the reaction coefficients we have here. So remembering that our chemical formulas will tell us how many of each one we have, that will put some information about your particular ions in the solution. So just don't forget about that. Okay, so that just kind of a quick little addendum just to make sure. Alrighty. Any questions on this solution business before we move on to thermochemistry? Okay, so as you guys have questions, I will just start here. Oops. Oh, there we go. Yeah, so if you had, for example, 0.1 molar of aluminum chloride, it would be 0.3 molar Cl. Or if it was like iron 3 chloride or something, yeah. If you had 3 chlorides, yeah, it would be 3 times. So I'll just write that. That's, oops. So just what you said. Technically, yes, you could do that. Shane, that would definitely work. It's very similar to empirical formula, right? Oh my goodness. What is all this? Yeah. So that would be how you would set that up. Yeah, absolutely, Starlord. Perfect. I just got scared because I saw this big old equation. And I was like, oh my god, no. But yes, that is the dimensional analysis, the unit conversion of how you would set that up. So your way of writing it is perfect. That is exactly how you would go around doing that. Perfect. Okay, so thermochemistry. We can break down this word, right? Thermo, for us, is going to be talking about heat, or broadly, energy. So we're going to be talking about some sort of energy things related to chemistry now. And so we're going to see that we're going to have a lot of fun doing math in this particular chapter. But as always, whenever we start a new topic, there are some vocabulary things to go through. So we can actually define energy. It's kind of, we know it's not matter, right? It does not have volume, it does not have mass. But more specifically, it's the capacity to do work, right? All of us here, we have very low energy. We don't want to do a lot of work, right? But scientists, we define energy as the capacity of something to do work. And so that leads us to another definition. Now we have to define what the heck work is. A work, typically, which is a W, is in physics defined as force times distance. And for that means it's the amount of force you need to do to move something a particular distance. So the amount of force to move something in a however far you're going to move it. All right, so thankfully this is not physics class, so I'm not going to make you do calculations like this, but I mean, technically it's an integral of force from, x equals 0 to wherever you end up, but let's not worry about that. So we don't need to bring calculus into this quite yet. So in fact, in Gen Chem, we're not going to really work with calculus at all, so lucky us. Cool, so that's how we're going to define work. And we have a fun law for us. The first law of thermodynamics is very similar to conservation of mass. Tells us energy cannot be created or destroyed. So we can't just come up with energy. Energy just can't leave. There always has to be a transfer of energy. So we're going to see that energy can take a bunch of different forms, but it can kind of just transform between those, but it can never just pop up or vanish. Okay, and we have a few more definitions. We're going to define a few more things. It's going to be easier for us to define. It's kind of hard to define these in words, but let's see if we can do it. The system is kind of what we are looking at. So that could be a reaction, a sample of something, whatever. It's whatever we're kind of focusing on. And the surroundings are going to be everything else. So that could be the air around it, or water if it's in solution, containers, whatever. It's just the other stuff. So if we're looking at, let's say, the coffee, if we are looking at this coffee, the coffee might be our system. Maybe we're looking at a particular molecule of this coffee. We're looking at the caffeine. Caffeine could be our system, and everything else is going to be the surroundings. So that means the water in here, the cup, the air on top, all that other stuff is the surroundings. And we're going to see that energy transfers between the system and the surroundings. And guess what? We have yet more definitions. We're going to see we can describe systems as endothermic or exothermic. What this means is that the heat or let me just describe this. So the surroundings are giving heat to the system. In an exothermic process, the system is giving heat to the surroundings. Yeah, totally. Especially like because it's written in like with all the carrots and stuff like that, it just totally looks scary. So let's look at a couple of things. This would be, for example, ice melting. In this case, the air, or whatever the surroundings might be, are giving heat to the ice. And as a result, that ice is going to melt. That is an endothermic process. And so we're going to see that that air could just be ambient air, or it could be heated up air. It doesn't matter. It could be air that's from a hairdryer, or maybe from a Bunsen burner or a stove, whatever. That air is warm, perhaps, and it is going to heat up that ice. It's going to give energy to that ice, causing it to melt. Some more endothermic stuff. That would be like sweating. And so, again, the air is going to be giving. Oh, hold up. Did I just mix that up? Sweating is endothermic. Yeah. Okay, cool. Sorry, Kevin, why you gotta do this? Spectator ions. Do. Typically, we surroundings. Yeah, surroundings. Yes. So spectator ions would technically be the surroundings because they're not really doing anything, right? They're just kind of there around it. Okay, so let's see, other endothermic stuff. This could be like, let's see, what else is a good endothermic example? That would be like sweat, so water evaporating, right? So the air is going to give heat to the water that's on your skin, causing evaporation. All right, and then same thing here, this causes melting. There we go. And in this case, the air or whatever is going to be our surroundings. And so the heat is going to be moving from the nearby area. Actually, what's a better example for the sweat would be like the skin. So your skin is giving heat to the water, to the sweat, causing it to evaporate. And in return, because that skin is giving away its heat, it's going to become colder. So the surroundings become colder. The system becomes warmer. So when you sweat, you cool down. That's the reason your body does it, right? So as your skin gives heat to that water, your skin, the surroundings, become colder. That's the idea, right? Your body is trying to cool down. So by doing that, that's how that's going to work. Exothermic reactions are a little bit easier for us to visualize because the surroundings are going to become warmer. So what's happening here is a combustion reaction reaction is going to heat the air. That's just burning something. Burning is exothermic. We are going to see that the surroundings become warmer and the system becomes cooler. So sweat is warm. That's the idea. So the sweat becomes warm, and as water warms up, it boils, right? This is happening like microscopically on our skin, right? So we're not actually boiling, of course, but we are evaporating that water. When we talk about intermolecular forces, we will see that the more, you have to heat up water to get it to evaporate, right? You have to put water on the stove, turn it on, let it go for a while to boil. That's the same idea here, is that we are trying to heat up something. That means we're making the system warmer, and as a result, something else has to cool down. So, yes, absolutely. But we see that that's the whole purpose behind all this stuff. But we see that if we have a fire, that fire is super hot, right? And the air around it is relatively cold. And so, by giving its heat away to the nearby air, they are going to equilibrate in terms of temperature. So, like, the closer the air is to that fire, the warmer the air is going to be, right? That's definitely how this is going to work. And so we're going to see, like you have just mentioned, that heat we'll learn about the other laws later. We're just doing terminology right now. So we know that heat will transfer from whatever is hot to whatever is cold. That's putting it in basic terms, right? So yeah, equilibration is going to be a part of thermodynamics that we're going to talk about, but not right now. I mean, yes, that's true. It would technically become a plasma if you heated it up enough, for sure. But what we're just working on here is identifying terminology. Another thing that we can talk about with exothermic things is heat is a product. So if you want to think about it in terms of a reaction, heat is going to be a product for an exothermic process. And for an endothermic process, heat is a reactant. So let's take our favorite combustion reaction. We're going to see that this is going to be exothermic. Heat is a product. For a combustion reaction, we are putting out heat, right? It is exothermic. We're going to see other ones like, for example, this particular reaction, this one is going to be endothermic. We need to put heat in to make it happen. So that would be another way we could identify something as exo or endothermic, is where the heat is on your reaction. By the way, heat takes the letter Q because that's the way that we've done it. And we remember work before was W. We're going to see energy is going to be a capital E, just so we can put all these happy variables out there. Okay, so we're going to see that we have ways of talking about all of these things, which are unfortunately, what's the word? Okay, let's look at an example, and then we'll talk about these. So here is a battery, and it is plugged in to a heating coil. And here is another battery that is hooked up to, I don't know, let's say a fan. How do I draw a fan? Oh my gosh. That's a fan, okay. What do fans do? Right, they move air, right? I don't know if you know this, but in this case, the change in energy as the battery is depleted, we're going to see, in this case, it's all equal to the heat. So the delta E is, oh my goodness, the kind of the full battery. Minus the, actually, we should do it the other way. Okay. We're going to see this battery's energy we're going to be able to talk about. And so that's going to be the battery at the final part after it's all used up, minus the initial amount of energy that the battery had. Okay, and so if we plug in our little space heater or whatever this thing is, it's just releasing heat. It's not moving anything. And so the change in energy is just going to be Q. It's just going to be heat. All the energy change is going to be heat. In this case, we're going to see that our fan is going to do some work. It's going to move some air around. However, I don't know if you've ever touched a fan, it does lose some as heat as well. So there's always kind of a loss of heat associated with most processes, whether that's friction or whatever. You'll always lose a little bit of energy as heat. However, we also see that we are doing some work, so some of the energy that we are going to use is going to be related. You could touch a fan while it's moving. I'm talking more like the motor, though. Like if you touch the motor of the fan, you'll feel it's warm, right? Or if you turn the fan off, it'll still be warm as it's like dissipating its heat. But yeah, so that's the idea. So the fan is using some energy to move itself around and push the air, and some of the energy is going to be lost as heat. What's interesting here is that if we think about the energy, let's say for this, oh my goodness, heating coil, let's say that battery had 100 joules of energy, just making up a number. We're going to see that it started at 100 joules, and eventually it reached 0 with the battery emptied. Yeah. Oh, I'm sorry. Did I not describe that? Delta, which means change in something. And that's always final minus initial. So it's the change in energy. The energy that it had before compared to the energy that it had now. All right, and if we look at that same battery now plugged into our fan, we're going to see that some of it is lost as heat, some of it is done or is used to do work, and it's the same idea here. So the amount of energy in this battery was the same. We're going to assume the same battery. But depending on what we're doing with that battery, we might lose the energy in different ways. For example, if you take your cell phone battery and you use it to heat up your pillow so that it catches on fire at night, that's one way you could use the energy. Or you could do it looking at memes in chemistry class. Like, you could use the energy in different ways, right? The idea here is that the energy is what is called a state function, which means it does not matter what pathway you take. It's always from one state to another state. It's defined. This may be somewhat hard to explain, so let's take a look at, I don't know. Okay, here. I'm really bad at drawing. I'm not going to draw this. But let's say here's New York, here's Los Angeles. Two cities, yes? They have a distance between them. Whatever that happens to be, whatever 3,000 miles, I don't know. We're going to see that this distance between LA and New York is a state function. It does not matter how you go from Los Angeles to New York. The distance between the two is the same. If you fly directly to New York from Los Angeles, you'll travel that particular distance. But if you stop in New Orleans or something, guess what? That does not change the distance between Los Angeles and New York. Right? Those two are still the same distance apart, no matter what path you take to get there. Your path can have all sorts of different things. We can see that distance traveled is not a state function. So if you go from LA to New Orleans to New York, that's totally possible, right? Maybe that's 1,000 miles and that's 2,000 miles. I actually have no idea. Or let me say there's 2,000 to each one. Your distance traveled depends on where you go, right? However, does stopping in New Orleans change the physical distance from Los Angeles to New York? No, like you're not moving the cities around, right? The cities are in fixed spots. They are in fixed states. So going between them, it doesn't matter how you get there. The distance is always the same. You might have distance that you're using to go to New Orleans instead, but that does not change the distance between them. We're going to see that the time traveling is also not a state function. If you walk to New York versus taking an airplane, you'll spend different amounts of time traveling, right? That just depends on what you're doing, your path. However, we're going to see that, again, no matter how long you take to go from Los Angeles to New York, they are still the same distance apart. So, just physically how far they are apart. Let's see. Another example. Okay. Let's see. We have Oz here on the bed. Can you see him? And there's a little bed over there, a little green bed. Actually, let me make this a little bit easier for you guys. Okay, so there's Oz. He's woken up. There's the little green bed. The distance between Oz and the green bed is 3 feet. Okay, so he could wander all the way around the room and end up in the bed, and he's only traveled 3 feet overall, just as a net. That 3 feet does not change. Doesn't matter how fast he goes there or by what path he takes, the distance between him and the little bed is 3 feet. Doesn't change. So we're going to see that this is the same for chemistry. This difference in energy for the battery, whether we used it in a fan or in that heating coil, the energy is a state function. It does not change no matter what we do with it. We could use some of the energy for work. We could use some of it for heat. Does not matter. Energy is going to be a state function. Okay, Q and W will not be state functions. But we'll deal with them later. And so we're going to see here that this battery had the same amount of energy. Doesn't matter. But some of it was now used to do work. Some of it was now used to do to be heat. And that's the pathway. So that's not state. Okay, but overall the total amount of energy is a state function. So looking at that in more depth, we know that we had two scenarios here. Oh my gosh, that's so ugly. Let's look at what these might look like. So if we ended up with 0 joules and we started with 100 joules, that means we have lost 100 joules of energy. When we think about this, using that energy to heat something else, as in to heat the surroundings, that's going to be an exothermic reaction, right? Remember, we're heating the surroundings. That's what we did with our heating coil. We heated the air around it. We're going to see that the change in energy will be negative. So we are giving away energy. And as a result, the amount of, yes, it's leaving the system, it's going into the surroundings. So either that's heat or it's work, or it's Oz moving around. That would be work, I guess, also. We're going to have that working. And so if you think about it, if delta E was equal to Q, what is that going to mean for us? Do we think Q is going to be positive or negative? What do we think? Any ideas? Hi there, Oz. What are you doing down there, little dude? Why is it going to be positive? If delta E is equal to Q, yeah, it should be negative, right? They're the same. If I'm saying if they're equal to each other, for an exothermic process, we're going to have negative heat. And so again, what this means is that energy is lost to surroundings. Or in this case, heat is lost to surroundings. And so we're going to have, Oz is just so cute. Okay. We're going to see that work will be negative as well. And we're going to see that that means that work was done on the surroundings. Another way of saying that is work was done by the system. So our fan doing some work, pushing the air, is going to be negative. So these are just conventions, and these are associated with an exothermic process, typically. Well, and then we can see what happens with endothermic. Guess what? Because these are the opposite, change in energy would be positive, change in heat would be positive, and the work would be positive. Right? Everything's positive for this. And so what this means is energy is gained by the system. Or rather, let me arrange this easily. System gains energy. All right, this means that system gains heat. And then this one implies that work was done on the system. And unfortunately, with the English of all of this, saying the same thing would be surroundings loses energy. A system loses heat, or work was done by the surroundings. So, unfortunately, English sucks, as we know. And so we can see here that these are saying the same thing. So basically, whatever happens to your system, the opposite thing is happening to your surroundings. So same idea up here is this one would be saying that the energy is gained by the surroundings. Or the surroundings are getting heat. So just words, lots of vocabulary. This is perhaps one of the trickier parts about thermochemistry in general, is understanding what's happening to what? Is your system gaining energy or losing energy? Is it gaining heat or losing heat? And so we have to kind of think about all these things, and we're going to relate these mathematically using these signs here. Fun, I know. Words. So let's take an example. So here is, I have a pot full of water. And we're going to have red fire because why not? Heating up, yes? We can go ahead and define the system as the water. And so that means the surroundings are the pot, the air, the fire, all that stuff is going to be our surroundings. And so we can see what's happening here is if we are going to boil this water, we are going to in order to boil that water, we have to heat it up, right? It's going to take heat from the surroundings into itself. And so let's try and describe it. So if the system gains heat from the surroundings, let's see what that means. If we look back to our, we're just looking at Q here, right? Do we think Q is going to be negative or positive in this case? Is our system losing heat or gaining heat? Yeah, right, it's gaining heat, which, as Shane has said, that means this is going to be endothermic, and Starlord says positive. This is great, you got all three of them. So we can tell that this is endothermic. We know Q will be positive. And what was the other one? It's gaining. Oh, we already wrote gaining, but that's what this is going to be. So if we were to describe this, we would also be able to say that this is a equation way of describing what's happening here. We have liquid water gaining energy and turning into a gas. And so we see here that the Q is going to be positive when associated with this reaction. So if we say it's going to take however many joules, that's going to be a positive number. So anytime we're talking about the system getting warmer, gaining heat, Q will be positive. All right, the opposite case, if it's giving off heat or it's releasing heat, Q will be negative. All right, so tomorrow we're going to work with how to calculate Q. Yes, that would work. That would work. Starlord, that is very a very good observation. However, typically in chemical reactions, we like to put things as everything with a plus. So what that would look like is you are absolutely correct. That freezing water would be the opposite process, right? But typically the way this would be written would be, we would just move the Q to the other side. Just typically that's how it's written. And that's how you would know that's an exothermic process as well, is because you see heat is going to be a product. So these two say the same thing. Yeah, so that would be one way you could look at it as well. Okay? Fun stuff. We have just talked about vocabulary for the past, well, it's not really, well, it is reverse technically also. Yeah, we could reverse the reaction, but I've just, like any other reaction, I've just moved one thing from one side to another. No problem. Just like any mathematical equation, if x plus 2 equals 5, we could move that 2 to the other side. No different. So, cool. Okay, I know lots of words today. The way it is. But look, we didn't have to do math today. Hooray. I guess we actually did maybe a little bit with that first stuff with solutions, but oh well. Okay, so next time we will continue talking about thermochemistry. We will get into some calculations. Do you? I like math more, but that's just me. Well, thankfully I'm the one in charge, so. Okay, with that, I'll see you guys tomorrow. I'll start looking at a thermochemistry homework. I don't know if I'll post one today, but we'll see. I also promise I will do some grading today. Don't know how much that will go, but I'll do something. So, cool. Thank you for your patience on that, by the way. So, cool. Okay, awesome. I'll see you guys tomorrow then. And don't forget, we will have class on Thursday as well. Yes, have fun indeed. Take care.